Once more, I want to know whether you're being able to hear me. Are you being able to see the screen?
Yes,
Yes,
sir.
sir. Yes, sir.
Right. So let's start. Although we could not do the we could not go to the stochastic hardware software partitioning approach. We have to shift in the interest of time. Today we'll have a brief look at another topic, system level analysis and design. So in the embedded system, uh, as we started by saying that first we have an idea of what we want to do in a very scratchy manner, and we try to jot that down in English language statements as far as possible, the functionality that we want to design as clearly as possible, uh, and then mm, right, as clearly as possible, and then we generate models from that, which ultimately percolates down into a task graph. Using that task graph then is partitioned into hardware or software. So in general purpose processors or software. So that was what we did till now, and we looked at hardware software partitioning. Now this is what we looked at. Again, we have seen this slide before. This is what we have looked at. So we are given a task graph in which containing a set of tasks for an app, for a controller, and those set of tasks will be mapped to a set of hardware artifacts, and mapped to also with a set of software artifacts. For example, the scheduling algorithm being a software artifact, the processors being an hardware artifact, the communication protocol being a software artifact, the communication medium per se being a hardware artifact. So that's part of the design. So here in this example, as we showed earlier as well, that I have a set of say 5 tasks in which I have mapped uh, I have mapped task 1 and task 2 on a general purpose processor. I have mapped task 5 and task 3 on custom hardware, which we could also say as a single purpose processor. If CPU is a general purpose processor, a custom hardware, as I said, will be a customized application specific integrated circuit, or ASIC, which will be developed in the form of a chip for that functionality itself, and therefore it can also be referred to as a single purpose processor against a general purpose processor. And you could have various options in the middle of a completely general purpose processor and a completely single purpose processor as well. For example, FPGAs, for example, these co-processors, or SIM, the single instruction stream multiple data stream processors, digital signal processors, to say to give us a few examples. So this is the way we have mapped the tasks. We also require the tasks also require to communicate among each other. As we said that I have a task graph, and that task graph communicates with other tasks. The tasks in them communicates with other tasks, and for these edges, I am transferring data, and this data, if 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 this task and this task, say task T1 and task T2, they are on they are on two different processors, say this is T1 and this is T2. If they are on two different processors, then the data needs to pass through a communication medium, and that will require a bus communication for it, and hence will incur additional overhead. And because this bus is shared among multiple tasks, so this bus has to be scheduled properly. That means the communication has to be scheduled, so that the one data communication does not conflict with another data communication on the bus. Now all these are designs. Now on this design we need to do analysis, and that analysis will have to say that given this design, will I always meet my performance goals? So such validation or analysis for real-time systems are almost always needed to satisfy constraints on time. And therefore, it is very important for real-time systems because most control systems are real-time. They have restrictions on time. They need to perform activities within deadlines, and hence they are real-time. So, um, So, uh, so the analysis has to check whether in the worst case scenario, whether even in the worst case scenarios, given the design that I have done, given the amount of resources I have allocated, hardware resources, bus resources that I have allocated to my tasks, the scheduling algorithms that I have put in place in that for that scenario, does it meet end-to-end performance goals? For example, let us say that I have an application which takes streaming input data continuously. For example, sensing the speed of the car every 150 milliseconds. It goes on taking data and it goes on producing actuation outputs. Now, let us say if such a control system acquires data at the rate of n samples per second, can we ensure that each data item will always be processed in less than 1 by n seconds? Why is it important or not important to decide that? Will all why is it important to ensure that to get an understanding of whether all my data items will always be processed within 1 by n seconds, even in the worst case scenario? For example, one such scenario where this could be very essential is that if you can ensure that all your data items will always be processed and the actuation will always be produced within 1 by n seconds, then you will not require buffers at the source or at the destination. You will not require buffers to hold unprocessed data items, right? Now, how can buffers help? Suppose if you're saying that you are receiving data at the rate of 1 by n seconds, but and on an average you process the data within less than 1 by n seconds, but sometimes you overshoot and take more than 1 by n seconds. So for those cases, when you overshoot, your previous computation may not have completed. So your next instance cannot start. So this task is executing every 1 by n seconds. So the next instance of the task can only start after the previous instance had ended. Why? Because you have allocated resource for one task at a time, one task instance of that task executing at a time. Now, if the processing of the previous input has not completed, the next input, the processing of the next input cannot start, and hence the input has to be buffered. You understand that if on an average it is less than 1 by n seconds, and the total number of times for the total amount of time by which this overshoot can happen, it is not the sorry, I'm saying on an average it is less than 1 by n seconds. What is less than 1 by n seconds? The amount of time it takes for a task to process the data for a given task. To process the data is less than 1 by n seconds, but I'm considering the scenario where sometimes it takes more than 1 by n seconds. For those cases, I have said that it may need to process, it may need to buffer the data, unprocessed data. But that buffer size will only remain finite if I have a bounded overshoot of this 1 by n. Otherwise, it will not remain finite. So even for that estimate to have that what is that finite sized buffer I will require, I need to do an estimation. And we understand that in many resource constrained embedded systems, for example, say in a spacecraft, I I require it to be the design to be as accurate as possible, right? So that if my design is accurate and I do for that worst case design, then I may not require buffers at all. So the risk cost with respect to the buffers is not wasted. For the buffers is not wasted. So I need to do a correct, good analysis on the time it will take for tasks to execute, even in the worst case. Okay. But the next point is that finding accurate estimates of time is not so easy because, for example, why? Because such analysis on how much time, how much end-to-end time an application is going to take depends, this timing behavior has to be conducted on the face of multiple problems, multiple interfaces. For example, microarchitectural constraints. What do we mean by microarchitectural constraints? For example, what is the pipeline structure of my of my system? What is the pipeline structure of my processor? How does pipeline structure help? Let us say that to process one instruction, you require k cycles. Now, if you have a k stage pipeline, on an average, you will require one by means one cycle. Suppose on an average, an instruction of the processor takes k cycles to execute. If you have a k stage pipeline, on an average, you will take one cycle to execute. But that again, on an average. Do you have reordered execution buffers, out of order executions? Why? Because sometimes what happens is that when you have machine instructions one by one, suppose a future machine instruction is independent of the current machine instruction. One is calculating A equals to B plus C, the other is calculating D equals to E plus F. So A equals to B plus C is independent of D equals to E plus F. So I can execute one before the other. Let us say D equals to E plus F, all my inputs are available on registers. A equals to B plus C, all my instructions are not available. Out of order execution processors allow D equals to E plus F to execute before A equals to B plus C. Why? Because the throughput will increase. The number of instructions processed per unit time will increase. But that adds to, although the average throughput is going to increase, you understand that predictability gets destroyed when you have such micro-architectural interfaces. So my point here is that you have to do an analysis of the time in the face of such micro-architectural interfaces. You have to understand what micro-architectural interfaces are there when you are doing this analysis. You don't have to do just now. I'm trying to impress upon you that people do such separate analysis for safety critical systems. You don't have to do in your second year or third year, but at some point in time, you may need to do such analysis. Okay. There could be problems caused by resource contention among programs running on the same processing element. We saw that there were two tasks. For example, here, there are two tasks which are executing on the same processing element, and you need to correctly schedule the task on this processor to ensure that both tasks meet their deadlines for all its instances. They will never miss, none of the instances of either task T1 or task T2 will ever miss their deadlines. You have to ensure it through proper scheduling, because two tasks, both these tasks are using the same resource. Therefore, proper scheduling algorithms, and we'll see examples of such scheduling algorithms in the next class. Okay. Resource contention among programs running on different processing elements have to be sorted out. Resource contention has to be sorted out, and this is done through multiprocessor scheduling. What I'm saying, that you have a group of n tasks running on m processors, and you have to schedule these m processors and multiplex the execution of these n tasks over these m processors together, such that none of the instances of any of these n tasks ever miss their deadlines. This is what is the problem of multiprocessor scheduling that has to be correctly conducted, and we have to obtain estimates on time for that. Given that scheduling algorithm, we have to ensure that contention due to large level caches are taken care. Why is that this very important to ensure? Because the main memory is about 50 times lower than your cache, while your latency, even for the last level cache, is within say 10 nanoseconds. When you go to the main memory, you require 70 to 100 nanoseconds or even more. So you don't go to the RAM. You want your data to be always available on the cache. So you want the number of cache misses to be as less as possible. But depending on the locality of reference of your program, that means how frequently the the data that you are currently used will be again used in future, or how frequently the data around the data that you are currently accessing will be accessed in the future. That is called locality of reference. Based on that, your hit or miss on the cache is going to vary, and such and this property can hugely differentiate, make a difference on the execution time of your task or program. Now therefore your design must include proper sized caches. Your The size of the cache should be such that it is able to properly handle your data based on the locality of reference characteristic of your right. So therefore we need to consider contention of these tasks with respect to last level caches. Why do I say last level caches? Because you have multiple layered caches, right? Typically L1 cache, L2 cache, L3 cache, you have caches like that. Okay, even if you have not studied cache memory till now, don't bother, just get these, there will be no questions on this, just get these ideas currently. When you study, you will get to know. Again, communication time over the bus or interconnection network is also important to analyze. As I said, that these tasks may need to communicate data. Task 1 may need to communicate data to task 3. If you have a system like this, right? For this communication, you will require communication over the bus. And again, as I said, as the bus is shared, I need to properly schedule it so that all my times on the bus are correct. Okay. And then there could be asynchronously coming interrupts from peripheral devices. When your program is running, you could be interrupted by other peripheral devices, and for that you may have to incur non-deterministic data on the task that is currently executing on the processor. In the face of all this, you have to correctly estimate the worst case time that your task is going to take, such that everything is planned, nothing happens abruptly during execution. You plan for the worst case behavior and you meet all your requirements. You assign resources in your design, you assign resources to each of these tasks according to your worst case scenario, so that you can always meet your worst case. This is what timing analysis is all about. Any questions till now? No? Yes? These are all stories, by the way, nothing. If you have some questions, I can answer. Hello, are you being able to hear me?
Sir, can you just explain the second last point once more?
Communication times over bus?
Yes.
Yes. So I am saying that, see, you are facing contention for processors like the CPU, because multiple tasks are executing the same resource, same CPU resource, and you are doing task scheduling. So also you have to do bus scheduling. Why? Because these tasks, I have said that these are precedence constraint tasks, and let us say task 1 is communicating data to task 3. For example, here task 1 is communicating data to task 3. Then you will require, because task 1 and task 3 are on different processors, you will have to communicate over the bus this data. And therefore, whenever task 1 needs to send to this data to bus 3, task 3, the bus should be available for that transfer, or I have to schedule that transfer of this data on the bus in such a way that the end-to-end time goals of the tasks are not violated. Because if until task 3 gets the data, task 3 will wait, it cannot start. Task 1 completes, sends the data to task 3 at a time which, when the bus has scheduled this communication on the bus, right? And the bus has to schedule the communication on the bus, this data communication on the bus, in such a way that task 3 can start at an appropriate time, and then it should also be able to complete on time. Right? This analysis has to be conducted, this end-to-end analysis. Suppose one bus is not sufficient, then the design should include another bus two buses need to be there. If one bus is not sufficient, even through scheduling. So the bus scheduling has to be correctly done so that all tasks meet their end-to-end time goals. Is it okay with you now?
Okay, sir.
Yeah, right. But again, as we told that such system level timing analysis is not very easy. Getting a tight analysis means a closeness, a closed, a tight analysis on the bound on time is not very easy. Why? Because even a single instruction, just consider a single machine instruction executing on the CPU, that the time for that instruction also will vary vastly on the microarchitectural features that we just talked about in the last slide. I'm just elaborating on that, how even a single instruction's time can vary due to microarchitectural intricacies or features. So for example, suppose you have an instruction cache. So your L1 cache is divided into an instruction cache and a data cache. Instruction cache holds the instructions of your program. Data cache holds the data of your program. Now, your instruction could be a hit or miss. Your next instruction could be there or not there on the cache. Why? For first time that instruction is fetched, it may not be there. But many a times the same instruction is executed again and again. For example, in a loop. So you have a loop many a times, and then you prefetch instructions. Suppose you are executing inside a loop, the next 6 instructions will be prefetched into instruction cache. Instruction cache apply prefetching. But then, even in the presence of that, you may or may not be your next instruction may or may not be a hit or miss on the instruction cache. Depending on your time or the time taken to fetch the instruction will vary. Your operands may be a hit or miss on that. Depending on that, your time to fetch the operands of that instruction will vary. If it is a hit or miss on the data cache, so you have a L1 cache miss, and then you have to get to L2 for that case. Whether there are pipeline stalls due to data dependencies. For example, you may not have studied, but there are read after write. So you read after write, that means your current instruction can read the data of your current operand, read the data corresponding to your current operand only after the previous instruction has written the output of its written the output of the previous instruction on that data. So suppose there is a data dependency between two instructions, and because this is pipeline execution, it does not happen that the next instruction starts only after the previous instruction has completed. The previous instruction has partially executed and the next instruction starts, because these are pipeline. It is not unit by unit that is executing. So it may so happen, if the data of the next instruction is dependent on the output of the previous instruction, the next instruction cannot start just because the previous instruction has not completed generating the output of that data. So there will be stalls in the pipeline. Stalls in the pipeline means one stage of the pipeline cannot proceed for us for certain amount of time because something is not available, something is contending. So if you have got an idea, that is sufficient. I will not ask questions from here. It may fail due to data dependencies or resource contentions from other instructions. And there could be branch predictions errors. Branch predictions could be right or wrong. So what are branch predictions? Suppose there is an if statement. If something is true, you go on one side. If something is false, you go on the other side. Even on the processor, you have conditional jumps, right? If you based on a condition, you will go once, you will take one path, or if your condition is false, you will take another path. Now, what processors do is try to predict which path will be taken. Why do they predict? Because depending on that prediction, it starts execution of the next instruction on the path that it predicts. But if your prediction is wrong, you have to backtrack to the other. So if you have partially executed the next instruction by predicting that your branch, but then actually it so happens that your branch is false, and you have predicted that your branch will be true, and in the predicted path, when the branch is true, you have started executing the next instruction on that path. So that instruction has to be flushed out. Instruction will have to go and execute the false path and the instructions in the false path. So what happens here is that if your prediction is wrong, it takes more time. If your prediction is correct, then it goes on. Means so which such prediction algorithms work. They are very interesting nowadays. As well, real story. So if your prediction is correct or wrong, instruction can take. Did not get the question once more. I have.
Sir, you are not audible.
Sir, sir, your voice is not coming.
Hello, hello. Are you being able to hear me?
Yes,
Yes,
sir.
sir.
Yes, sir, we can hear.
All this time you could not hear me at all. Since the beginning of the class, since the last half an hour, you did not hear
No,
me.
sir, for the last 5 minutes.
No, sir.
Oh, how can I suddenly muted? Have I been muted by somebody else? Is it possible that somebody else has muted me?
Sir, it is possible, but also your voice is sometimes cracking in between.
Okay. Okay. But I don't expect somebody just muting me. I'm trying to take the class to the best of my ability. That's all I can say. Yeah. So let's start. I'm muted again. Please let me know very quickly so that I can change that. Okay. So what we try to impress upon is that timing analysis is very difficult. Even the time taken by a single instruction can vary vastly due to multiple factors. Now, another example to show why timing analysis is important, and we must schedule or do an analysis of time based on exactly the behavior that we have intended to. And if whatever we have thought is not according to what we had intended, then the expected output can be different. For as a small example on that, let us consider four processes C1, C2, C3, C4. I have four processes C1, C2, C3, C4, C3, and C4 on four processing elements. For simplicity, I have all separate processing elements for each of these tasks, for each of these computations. And they are connected to a single bus. I have a single bus, single. And the bus scheduling policy is also very simple. P1 has the highest priority, then P2, then P3, then P4. So if P1 has some data to to send on the bus, P1 will always be able to send. If P1 if P1 is sending something, P2 cannot send. It means P2 can only send if P1 has nothing to send, and likewise. And message transmission on the bus takes only 1 unit of time, and that is fixed. And all the tasks take the same amount of time. For example, C2 takes three amounts of time. The lower bound and an upper bound is three for 3 amounts of time for C2. Only C1 takes 3 amounts of time in the best case and 4 amounts of time on the worst case. And why does such time can vary? Why can such time vary? Because depending on the data, the program could be executing different control paths. The actual set of instructions executed within the program can be different depending on the data, because there are control paths, right? Because you have if then else statements, etc. You can have loop bounds based on the input data. That is why your program can take different times. Right. So then you have found out that the lower bound on your time, which is the best case execution time, is 3, and the worst case execution time is 4 for C1. All other times are fixed. For example, C3 takes 1 unit of time, both in the best and worst case. C4 takes 2 units of time, both in the best and worst case, and C2 takes also 3 units of time, both in the best and worst case. And the processing of these tasks happens like this. C1 executes and produces message M1. After this message M1 is received, C3 can start. So C3 depends on the data sent by C1. Similarly, C2 starts in parallel, and after C2 completes, it generates message M2, which is received by C4, and C4 can only start execution after it receives M2. After C4 completes, this message M3 can be generated and the whole set of instructions complete. Right? This is what this is all about. Now, we will consider case C1 takes 3 units of time, because that is the only thing that is varying in this whole. In one case, when C1 takes 3 units of time, case when C1 takes 4 units of time. So this one is the scenario when C1 takes 3 units of time, and this one is the scenario when C1 takes 4 units of time. Okay. Are you in slide number 6?
No, sir.
Oh my God. Just a minute.
So your
I
voice
am
is
in
cracking. Maybe some internet issue.
maybe. Maybe. Ah, are you there with me now? Is it better?
Yes, sir.
Okay. Right. So see that if you are there in slide number 6, I have drawn a red line, and one case is C1 equals to 3, the example for which C1 takes 3 units of time, and on the right side I have the other part where C1 takes 4 units of time. Now, when C1 takes 3 units of time, I know that C2 always takes 3 units of time. So this one is processor P1, processor P2, processor P3, processor P4. C1 executes on P1 as shown, C2 executes on P4 as shown, C3 executes on P2, and C4 executes on P3. We have seen, right? Let us say these 4 processing elements are one is the anti-lock braking system, other is the fuel injection system, the other is the cruise control system, and the fourth is the power window system. These are 4 things, and these 4 tasks are running on 4 different processors, their own, and this sort of message passing is happening. Now, when C1 and C2 both takes 3 units of time, both complete at time 3 on the bus. Both complete at time 3 on process C2 completes at time 3. C1 also completes at time 3. C1 completes on P1 at time 3. C2 completes on P4 at time 3. So, and now, so both generates message M1 and M2 is generated at the same time at time 3. Now, because M1 has higher priority, why M1 has higher priority? Because we said that for buses, P1 has higher priority than P2. So if P1 has a message to send, it will be able to send. P2 will only be able to send as P1 has not is not able to is not there on the bus. P1's data is not there on the bus. So now what has happened is that both P1 and P4 has messages to send, and therefore P1 has a higher priority. So M1 has been sent. M1 has been sent, and M1 completes at time 4. And after M1 completes, M2 starts on the bus, and it gets on to processor P3 at time 5, and M1 reaches processor P2 at time 4. Just P2 at time 4, the task C3 can start executing, and task C3 takes only 1 unit of time, so it completes execution at time on processor P2. And then what happens? However, this task C4 on P3 can only start after M2 reaches processor P3, and that happens at time 5. So C4 starts executing on processor P3 at time 5, and it takes 2 units of time, so it completes at time 7. After it completes, after C4 completes, the message can be generated. After C4 completes, that message is generated, and the whole thing completes at time. When C1 takes 4 units of time, so on P1, C1 executes and completes at time 4. On the other hand, C2 executes and completes at time 3. Because C3 has completed at time, C2 has completed at time 3, the bus is empty at that time. Nobody is asking for a bus at that time, and the bus is empty. So M2 can start its communication. So M2 starts and completes at time 4. And then because M2 has completed at time 4, then computation C4 can start. Computation C4 can start because M2 has been received on processor 3. So C4 can start, and then C4 takes 2 time units to complete. Now at time 5, you see M4 this M2 completes at time 4. So the bus becomes empty again at time 4 when C1 completes. Now C1 completes, and the message M1 can be transmitted over the bus, and at time 5, at time 5, this M1 reaches processor 2, and C3 can start after M1 has reached, and C3 completes at time 6. Okay, C3 completes at time 6, and on the other hand, C4 completes at time 7. Sorry, C4 completes at time 6, and the message can be transmitted and completed at time. So what we see here is that when C1 takes less time, the total amount of time required for the entire process to complete is higher, 8 time units. When C1 takes more time, then the total amount of time required to complete the whole process is less, which is 7 time units, right? So here is a timing anomaly, that when your computation takes more time, your total amount of time required to complete the whole process is actually less. Why? Because of the scheduling policy in place, because of many other factors. So the point is that this means that we need to accurately calculate the upper bound on the time taken for each task, and then generate all the scheduling policies that are in place based on that upper bound and stick to that upper bound. Even if a task takes less than that time, you should not have because you have planned for that worst case times, and you know that if those worst case times are satisfied, your timing properties with respect to your system will never be violated, because you have planned and generated your schedules according to that, right? So therefore what we are pointing out here is that estimation of the execution times of programs, correct estimation of the execution times of programs are very important to determine how much time a task will take to run in the worst case is very important. And tighter this estimate, lower will be the amount of resources required for the entire system, because you are saying that you are planning and scheduling for the worst case, because so that you always go as planned according to what happens even in the worst case. Now if your worst case is a bit better, then the amount of resources that will be wasted for due to your planning for the worst case will be less. That's the point. Any questions here? Any questions? Are you being able to hear me?
Yes, sir.
Okay. Okay. Now, okay. So what we said here in the last slide is that system level analysis typically considers delays due to possible contention and preemptions across tasks, right? So because there were contentions among tasks on the processors and on the buses, you had problems in the estimation. But for all those estimation to start, you need to have a correct estimation of the time that is consumed by a single task. So let's try to estimate the execution time for a single task first. Now, what is a task? A sequential piece of code. It is important to analyze the worst case execution time of task, WCT, worst case execution, or the upper bound, which is an upper bound on the execution time. Now, there are two ways of estimating that. One is through simulation for a particular platform. Now, how do you simulate? You execute the task for various possible inputs and then find out what is the time taken in the worst case on that particular platform. But that may not be accurate. Why? Because the task may have several different inputs, may have infinitely different inputs that it can actually be faced with. The task may be faced with inputs which you have not foreseen during simulation. Many a times it is done through simulation, but for many safety critical systems, it is not done. Why? Because there are chances of inaccuracy over there on the estimation. And also the platform on which that code will execute may not have been fixed when you are doing this analysis. So something called static analysis or a mathematical analysis is adhered to. Now, why is estimation difficult? Simulation based estimation, because a program can have infinitely many inputs. An image processing program can take any image as input, and if there are multiple control paths depending on what type of image processing you want to do, you want to sharpen, then you want to let us say different types of filters you want to apply, you want to reduce the size of the image. Depending on that, an image processing program can take various amounts of time on the given type of image that you have, and therefore it is very difficult to find through simulation what will be worst case and best case estimation time. Now this example was not great in the sense that because image processing may not always be a safety critical application, a part of a safety critical application, such analysis, even if there are violations, even if you are inaccurate on determining the upper bound, it may not be catastrophic. But in many safety critical applications, let us say a nuclear plant, if you are bound on time, the estimation on the bound of time is not accurate, you may have a catastrophe. So a correct estimation is required for many safety critical systems. Now, how do you do? Now, to do such analysis, you do something called static analysis. To get an estimation of the execution time, you do something called static analysis. Now, static analysis takes as input the control flow graph of a program. So what do you mean by the control flow graph of a program? It's a directed graph whose nodes are basic blocks and whose edges denote control transfer across basic blocks. And what is a basic block? Basic block is the maximal code fragment executed without branching of control flow. That means basic block is a sequence of code in where are you, by the way? Which slide?
The slides are just changed. Means we were on 7 and just changed to 8.
Cam still 7.
You're in still 7. I am actually in 8. So we have started with static analysis, and we say that to do static analysis, we first create the control flow graph of a program. From the instructions of the program, we generate control flow graph. And I'm trying to explain you how control flow graph of a program is generated. So control flow graph groups the program instructions into basic blocks and transfer of control between basic blocks. Now, what is a basic block? Basic block is a set of instructions. So what is that? What is the property of that set of instructions of a basic block? It is that sequence of instructions which does not involve branching of control. That means if the first instruction of that code is executed, there will be all those instructions in the basic block will be sequentially executed one by one. There will be no branching of control. There will be no if statement, for example, inside the intermediate instruction of a basic block will not have. So there will be no branching of control emanating out of the basic block intermediately, and there is no branch, no control that is coming into from other places. There is no branch instructions whose target is one of the intermediate instructions of that basic block. So whenever you enter the start of the basic block, you are guaranteed to exit out of the basic block through sequential execution of the instructions inside the basic block, right? Now, how do you create? What is the algorithm of creating a basic block given a program? Very simple. So the first instruction of the program is always the start of a basic. So what you do, the algorithm finds out which are the instructions that can be the start instructions of the basic block. Okay. So now, again, what I'm trying to explain you, how do you generate the basic blocks of a program? How does this algorithm proceed? You determine the start instructions of the basic block. Why? Because when you go through the program code, if you are able to determine the start instruction of a basic block, you know that a new basic block has started, and you go on putting instructions in that basic block until the next start instruction of another basic block has been encountered. So what is important is to find out who could be, which instructions of this program could be the beginning of a basic block, right? So this is what we want to find out. Now, which instructions could be the beginning? The first instruction of the program firstly is always the beginning of a basic block. Okay. Then if your program is if you have a branching of control, if you have a branch, if you have a if statement, right? Or let us say the opposite. If your next instruction is the target of the branch instruction from some other place in the program, that means that you have a branch instruction at some other place in the program whose target is your current instruction, right? Go to this label. Now this label is a line number which has an instruction, and let us say your current instruction is that label. So you are the target of your next instruction is the target of a branch instruction. So if you are the target of a branch instruction, then this instruction is the beginning of a new basic block. So your target went on including next instruction, the next instruction, the next instruction inside your basic block. Now you have encountered an instruction which is the target of a branch instruction. So now your previous basic block ended, your new basic block has started. Okay. And if you have an if statement, then the next instruction to that if statement, or if you have a branch statement, which is, let us say, control flow branch statement, like an if statement. Then the next statement to that if statement is also, if you have a condition, then the next statement of that condition is also the beginning of a basic block. Let us see, for a simple code that we have here, how do we determine the basic blocks. So what is the code I have? Sum equals to 0. For I equals to 0, I less than 10, I plus plus. If I percent 2, that means I percent 2 equals to 0. So I percent 2 equals to 0 means it's a even number. If I is an even number, you do sum equals to sum plus 1. If sum is less than 0, you return. So this is the simple set of instructions that you have in this program. How do I determine the basic block? See that the first statement is the beginning of a basic block. So sum equals to 0 is a basic block. The next instruction is I equals to 0, part of the for loop. So that is also part of the first basic block. Condition. That condition per se is not the beginning of a new basic block, but that condition is a basic block. Why? Because that condition is also the target of a branch. See that if you see in this, if you see this program here, this control flow graph here, you see that from block number 6, from basic block number 6, you come back to basic block number 2, which means that this condition is also the target of a branch. So therefore, this branch has become the start of a new basic block. Okay. Now, because this is a condition, your next instruction becomes another basic block. So I percent 2 is another basic block, right? And then your sum equals to sum plus I. Are you there with me? Your I percent 2 is a basic block, and because this I percent 2 is a condition, so if I percent 2 equals to 0, you do something. If false, you do something else. Hence, you have another basic block, because this is a conditional statement. So the next statement is another new basic block. So sum plus I becomes another basic block. Likewise. Okay, so you generate a control flow graph in this way. So the first instruction is always a basic block. Then all subsequent instructions get included into the basic block. If you encounter a statement which is the target of a branch instruction, you have a new basic block. And then if you have a conditional statement, the next instruction to that conditional statement is also a new basic block. These are the 3 simple rules for generating basic blocks, and there are no other rules. So the only thing that you have to view is you have to break down this program into simple fragments. You cannot see the for loop entirely as a single statement. The for loop has 3 parts. One is I equals to 0, if I less than 10, and I plus plus. So therefore, I have an I equals to 0, which is initial and is always taken. I have an if I less than 10, because only if I less than 10, otherwise and then you have an I plus plus, which is another statement which comes at the end of the for loop, right? So in between there are other statements. You have to look in this way. If I percent 2 equals to 0, that means if it is an if statement which has a true part and a false part. If I percent 2 is equals to 0, you take one path. If I percent 2 is not 0, you take another path. So likewise, you generate basic blocks. Now you also don't need to remember, I won't give you questions on this, how to generate basic blocks. But if you have understood and got an idea as to how basic blocks are generated, that is sufficient for me. So essentially, given a program, how do you generate your worst case execution time? See the procedure here. First, you find the worst case execution times of basic blocks individually. Okay. Then you compose the worst case execution times of basic blocks according to edges in the CFG and calculate the worst case execution time of the entire program in that using this. And then and how do you do this? Using an ILP. So this ILP we will study and finish off. In the next 15 minutes or so, we will study this ILP, and that's all I will say. Okay. So let us see how to execution time through static analysis. Now, to do static analysis, we are taking here, for our case, we are taking a few simplistic assumptions. I am in slide number 9, by the way. Have you gone to slide number 9?
Not yet, sir.
No, sir.
No, sir.
Just a minute. You should go, then we will start. Now I think you have gone, right?
Yes, sir. Just now.
Yes, yes. So we will assume. So what are we trying to find out? We are trying to find out the upper bound on the running time that a certain task or program will take. Because we said that determination of this upper bound on time is very important to do an end-to-end analysis of the time the overall my controller is going to take. And that analysis is essential to ensure that all my deadlines will always be met in all cases. So the all that analysis fundamental boils down to first understanding what is the upper bound on time of a single task. That is why we are trying to find out the execution time of a single task. And we said that finding the execution time of a single task is difficult through simulation, because simulations mean that you have to actually test the running time on various inputs. And many programs can have infinitely different inputs. And if you have a complicated program, it is very difficult to estimate how much time this code can take. And therefore, there are mathematical formal mechanisms of estimating the running time of a program. For those formal mechanisms to be applied, you have to first break down the code of the program, code of the task, into its control flow graph. What is a control flow graph? Control flow graph breaks down the code into basic blocks and transfer of control between basic blocks. So if you see here, for the program that you had, you have got this control flow graph. It is a flowchart like structure, but this is the structure that you have for this program. First, you do sum equals to 0, I equals to 0. Then you do an if statement if I less than 10. If I less than 10, you go to I percentage 2. Then you again have two paths over here. So if you can, you can see that this control flow graph represents the logic of your program. Now, given this control flow graph, what is the approach for finding the worst case execution time? We first find the individual worst case execution times of each basic block. And why is that easy or relatively easy? Because we are assuming, because we know that each basic block is a sequential piece of code which will always run one after another. There is no loops or conditions. So once the flow enters into that basic block, it will always execute. So if in the absence of complicated microarchitectural intricacies, which will always be taken inside in the basic in the ILP formulation that we are in the static analysis, but for our current case, we will not consider that. We will see up to this only, simple. We will remain up to the simple case. For this simple case, we want to find out how the worst case execution time of this entire program can be found out. So firstly, we have to find CI, the execution time of each basic block. So this is the worst case execution time. The CI is the worst case execution time of basic block I. Give this, therefore I find what is the execution time of basic block, because it has just two statements, and we have assumed that each statement has, for simplicity, for our analysis, for simplicity, this is not the actual case. For simplicity, we have assumed that each statement takes 1 unit of time. So basic block 1 takes 2 units of time, and see all other basic blocks take 1 unit of time. All other basic blocks take 1 unit of time. Why? Because all other basic blocks have only one instruction. Only the first basic block had 2 instructions. So that is why C1 has 2 units of time and all others have 1 unit of time. So C2, C3, C4, C5, C6, C7, C8 all are 1 time units. The worst case execution time of that basic block is 1 time unit. Now, given this, how can you find out the time by the entire program? Slide number 10. Are you there? Slide number 10. Yeah, now you're in slide number 10, right? Slide
Yes,
number
sir.
10? Yes, yes. So, given the worst case execution times of each basic block, what you only need to determine what is the number of times each basic block will be executed in the worst case. So let n1 n1 be the, let n1 be the number of times upper bound on the number of times basic block 1 can execute. N2 be the number of times upper bound on the number of times basic block C2 can execute. In general, Ni denotes the number of times basic block I can execute. Therefore, if this is n, the time that will be taken by the entire program can be given by whatever is written in this time. Time equals to summation of Ci into Ni. Why? Because Ci gives me the worst case execution time when the basic block is executed once, and Ni tells me how many times in the worst case or upper bound on the number of times that basic block can be executed. So summation Ci is the worst case execution time of the basic block if Ni is the upper bound on the number of times that basic block is executed. Are you with me? Are you with me?
Yes, sir.
Yes.
Yes, sir. Yes.
Okay. Okay. So understand now the ILP formulation. For the ILP formulation, this N1, N2, N3, N4 becomes my decision variables because I have to find out the upper bounds on those times. And C1, C2, C3 are known because I have already found out how much time these basic blocks need to take. And they are constant because I know that once control enters into the first instruction of the basic block, it will execute all the instructions in the basic block and only then it will execute. There is no branch of control in between. Okay. Now, given this, therefore, your decision variables are n1, n2, n3, and hence your objective function to the ILP becomes what? Your objective function becomes 2n1 plus n2 plus n3 plus n4 up to n8. Why? Because of the simple case that only your first basic block has and worst case execution time of 2. All other basic blocks have a worst case execution time of 1. So what is the upper bound on the time? 2n1 plus n2 plus n3 plus n4 plus n5 plus n6 plus n7 plus n8. This is it. This is your objective function. Now you want to maximize this. Why? Because you want to find out an upper bound on the time that it can take. Now how can you maximize? So I will maximize depending on a certain set of constraints. Constraints on what? Constraints on the decision variables. How can you constrain the decision variables? The decision variables can be constrained firstly by saying that, let us say, the first basic block can only be executed once and the last basic block will only be executed once. So N1 and N7 will be equal to 1. That is the first constraint. Now, will I be able to control my execution time of the program if I have only these two information? No, because the loop can be multiple. If the loop size is infinite, the program will take infinite time to complete. So I need to have an estimate on the bound of loop. So loop bound is essential to take into consideration. So what I am trying to say, what I am trying to do, given the objective function, I am trying to get constraints on the decision variables by considering the flow of control, how the control will flow. The first thing that I understood from the flow of control is that my basic block 1 and basic block 7 will execute only once because that is the start block and that is the end block. It will execute only once. In between, however, you still will not be able to generate a finite execution time upper bound if you do not consider loop bounds. So consideration of loop bounds are essential. Okay, but then how essentially do you want to consider? See this. how many times a particular basic block can execute, this ni, how many times an ni can execute is equal to the number of time control enters into the basic block. The number of times the basic block executes is equal to the number of time control enters into this basic block and is equal to the number of time control exits out of this basic block. So for example, if you consider, let us say this basic block 2, it is equal to the number of times control enters into 2 from 1 and plus the number of time control enters into 2 from 6. So N2 equals to E12 plus E62, where Eij determines the number of times control flows from node I to node J. Okay, if Eij denotes the number of times control flows from node I to node J, then N2 is equals to E12 plus E62. So that is what you see here, that N2 equals to E62 plus E12 and is also equals to E23 plus E27, right? E23 plus E27, right? Fine. Now, we know that firstly E12 is 1. Why? Because N1 is 1. 1 N1 equals to 1 and is equals to E12. So I know E12 is 1. That is one bound I got. The other bound which I got is that I has to be less than equals to 10. So the number of times E62 will be executed is 10. So the number of times this block C2, this block 2, basic block 2 will be executed is upper bounded by 11 because is E12 is 1 and E62 is 10, upper bounded by 10. So the number of times this basic block 2 will be encountered or will be executed is at most 11. Okay, but let's see in the next slide. I am in slide number 12.
Professor Sarkar, this is Somnath. Actually, I just wanted to remind you that from 9:15 the test will start.
Yeah. Maybe I'll overshoot by 5 minutes at most. Within the next 10 minutes, I'll complete.
No, no. The test is scheduled to start at 9:15. I have scheduled it actually. I had taken permission, so I have scheduled it from 9:15.
Can't you start by 5 minutes late? 5 minutes, can't it be delayed?
I don't know. I'll try. Then 1 minute. I'll just try.
I'll take 5 minutes to complete.
Sir, what is the duration for the test?
It'll be 35 minutes.
Okay, sir. Actually, some of the students have exams today at 10 p.m. So they have to log in by 9:50, something like that.
Okay, so I stop here and I'll start. I'll tell the next part of this on Monday, and we'll complete our course on Monday. Yeah, we stop here.
Yes. Sorry for that. And so are you able to see? Are you guys able to see the in the activity or in the activity or in the assignment? Are you able to see anything?
No, sir.
Okay.
No, sir.
Okay. Yeah, I mean there are 3 more minutes, but. Yeah, are you able to see? If anybody is able to see the link or something, please inform me. It should take it's 9:15. Yeah, just check now. So has it been posted?
No, sir.
No, sir.
What do you mean, no, sir?
No, sir.
What?
Sir, it is saying failed to load assignment.
Why? 1 minute. Why failed to load assignment? Here I'm able to see, right? I mean, 9:15. But can you check again?
Sir, it's not. It hasn't come yet.
Sir, it's not there.
So it's not there.
Okay, we are distributing your assignment to students now. Please check back soon. Okay. It gave me some message now. So it's saying that it is distributing them. Hmm. Okay, can you see it now?
No, sir.
No, sir.
What? Where are you checking? Are you checking in the activity or the assignment?
Assignment section. Like
Sir,
both,
both.
but
But why is this? Open Teams.